Welcome everybody to another video. Today we have an exciting guest. Tom and I actually chatted on formerly known as Twitter, now X, and I actually, found Tom's really cool GIFs and videos of his MD trajectories online, and I figured, you know what, it would be awesome to see this in VR and make a video together. So I reached out and now here we are making that video. So I guess Tom, if you want to do a little bit of an intro about yourself and how you got
Yeah,
started with these
sure.
simulations. Yeah, go ahead.
Sure. So I guess my history with nanotechnology goes back a long way. I remember vividly back in middle school when I first came across the term nanotechnology, and I had no idea what it was, and I did some research on it, and it was then that I basically took a vow. It's like this is what I'm going to do, right? This is seems like the best prospect for humanity and all that kind of stuff that you're into when you're younger. Then not much happened until I graduated from college with undergrad college, and I was wondering what's the best way to get into this, like machine phase nanotechnology. And then I realized there was a company basically right down the street from where I live called Nanorex. And at the time, Nanorex was producing this molecular CAD package called NanoEngineer-1. And Eric Drexler was their chief scientist, which is exactly sort of the brand of nanotechnology I was into. If you're into engines of creation or nanosystems or any of that stuff, it was perfect. So I went and I worked for them, and however, by then they had pivoted to structural DNA nanotechnology, which I completely understand. It's really cool stuff. It's a science and a technology for now because you can actually build this stuff. They're doing really great things in the field. But my heart was always in the more machine looking, mechanical looking nanoscale systems, right? So um, basically, I left Nanorex and went back to school, went back to grad school. And then after I got done with that, I was looking around and I came across Ralph Merkle and Robert Freitas's company, Nanofactory. And if you're familiar with their work, they've been in the scene since the scene started, basically. And they're all about diamond mechanosynthesis and building the types of machines that I was into. So I went and I worked for them. I worked for them for 10 years. My role with Nanofactory was basically to assume that atomically precise manufacturing capabilities are coming, that they would be achieved. And then once they're achieved, what should we build with it? So I was having a really great time designing a bunch of little molecular machines, and it was just a great experience. Then I left. I think that effort is still going on to some degree. Basically, just the lab portion to develop mechanosynthesis, which I think it's great. I wish them all the success possible because it's basically the best chance I have right now to get the stuff that I'm working on actually built one day. So this is where I am now. I've been basically an independent researcher for the last couple of years. I was having a lot of fun at Nanofactory, but I'm having even more fun now because it's more open, it's more collaborative. I get to do stuff like working with you guys and seeing all your neat stuff. And yeah, so that's it. I'm happy for the opportunity to talk about the work I've been doing.
Yeah, that's awesome. I mean, definitely, so much has been happening in nanoscale development that changed from the 80s and 90s when it was hyped in its own regard, and I think that
Oh, for sure. Yeah.
sci-fi took it a certain direction with gray goo and like
Yeah, I was a
these like
little
self-replicating nanobots that mess everything up. Yeah.
yeah.
I mean, we're kind of far off from that, but then the same side, we're also pretty, green goo could be another way to look at like a realistic version, because obviously you have ways to engineer viruses and bacteria and other, microscopic and nanoscale organisms that function really well. They reproduce. But getting a full synthetic like diamond-based thing to
Mhm.
somehow sequester carbon to like reproduce and become a gray goo cloud, like I think that's so far off. It shouldn't
I
really
think
be
it's
a
pretty
concern, right?
unfetched. I don't think it's very likely. It's
Yeah, but when you talk about nanotech with some people, they think it's like this is gonna happen. Like you hit the wrong
oh, for
button and
sure.
you
Yeah.
accidentally create the gray goo cloud of
There's a
nanobots.
lot of doomers in every field.
Yeah, yeah. But no, this was fantastic. Yeah, when I was in undergrad doing nano engineering, we had a project and I got really into graphene quantum dots. And we were trying to functionalize organic photovoltaics with graphene quantum dots to increase the efficiency. But as a thought experiment, can you just take a single quantum dot and like make a little like solar panel nanobot out of it? So that was kind of like a fun thing I thought about. It's like the reality is those things are hard to make. So as we get closer to real, atomic precision manufacturing,
Yeah.
maybe we'll be seeing some cool things like that in the future.
Yeah, I mean, working with the types of designs that I do has just given me such a great appreciation for the brilliance of nature. I mean, you look at the molecular machines of proteins
Yeah.
and how complex and beautifully they operate, and well, you can't come close to that. It's just it's a completely different type of field.
Yeah, yeah. I mean, I think that field's awesome, and obviously we do a lot in the life sciences and even some synthetic biology. But I really like the marriage of both of them, where maybe you have some assembled like DNA origami lattices that help other things to assemble that are inorganic, and
Oh
this
yeah.
becomes some sort of a bio scaffold with other things, and you make some sort of a system. I don't know what's gonna, it does something, and like you kind of combine both aspects of it.
Yeah, I would love to see the combination of protein design and just diamond NIMS, not even atomically precise diamond NIMS, but
Mhm.
just using the biological motors that already exist and work so well. Just somebody, combining those, which is basic, not even diamond, just silicon NIMS,
Yeah,
the biological and the artificial. I think that's a really fascinating field for sure.
yeah, definitely. Or even some of these like silicon nanopores, maybe like functionalizing that with protein structures and creating some sort of a vector, a synthetic vector. Like you talk about back in the day, they had that Fantastic Voyage movie,
Hmm.
Fantastic Journey, Fantastic Voyage. Um,
Voyage, I think this little
which
submarine.
everyone in nanotech talks about that, right? It's like, oh, what if you could zoom down and be like a doctor inside the patient and you like fix
Mhm.
all of their little problems from within? It's like, yeah, maybe something in that direction would be helpful to people. Some combination of life sciences and nanotech. Yeah, I mean, nanome as a name, right? It's the everything at the nanoscale. So it's all the little mers, the nanomers, all the polymers and parts and everything you would assemble. And so you have life science parts that you could assemble into proteins and peptide chains and RNA, DNA, or based organisms. Really, big toolbox. But if you add a little bit more to that toolbox, like we're saying here, maybe you could have some nanotubes and some little functional diamond parts and silicon spheres. So really, nanome as a whole is everything at the nanoscale. We don't exclude any atom types, so you could import any atom type on the periodic table. They're all just arranged in different ways. And so for the most part, we have been supporting the file formats of life sciences, PDB, MMSIF, SDF, smiles, all the stuff. And usually you could convert between file formats with a lot of the material science-based things. Like if you have a .cif and you don't want one atom or two atoms, you want 10,000 atoms. I can kind of use other tools like Vesta from JP Minerals to create little parts. Eventually, we'll be having more parts available, but right now I'd say we got our work cut out with just all the things that life science and drug development people want to see in the program. But again, we're not excluding the silicon and iron and gold and platinum and all these other fun things. It's just not the main thing that people use it for, but it is part of the Nanome vision.
So my understanding is that like the simulations that we're about to see today, they're like
Yeah.
Yeah.
impossible to physically manufacture today, but they
Mhm.
will be ideally, right? And like, so what is, the state of the art? I guess, and if you guys aren't familiar now, that's fine. But like, I figured like, how
Uh,
precise can we get today? I know that with
so with the diamond tech, I don't know. With and a lot of these things, if you don't care about every atom mostly, and you just mostly care about feature size, it looked like a lot of those diamond based components you had were on the order of like 2 to 10 nanometers, 2 to 5 nanometer, yeah, maybe like width and like we can make measurements in VR and kind of compare there. But if you look at silicon chips, I mean, with silicon in general, you hit a wall around like 3 to 5 nanometers where you just hit quantum tunneling and like incoherence, and you can't really compute much. But that's pretty much the limit that we're already pressing up against in terms of manufacturing. If you look at the specs, what does that actually look like? Are you able to construct a perfect 3 nanometer feature like a diamond spring? Maybe it's made out of silicon instead of diamonds.
Mhm.
Not really, not really. We're not quite there yet, but like we're kind of in a similar ballpark with current silicon fab tech. And then if you look at bottom up synthesis, yeah, you literally like, yeah, you have a chemistry experiment and you could start just building gold nanoparticles, and it's, from the atom up, it's just like, wet chemistry. So it's kind of similar to what you'd be doing to just traditional chemistry. So top down, we're getting close to that 3 to 5 nanometers, kind of, if you believe the actual like fab stuff, probably a little bit higher than that. And then on bottom up's always been atomically precise because it's chemistry. But in terms of the diamond spring, like maybe you can make one of them soon-ish in the next 5 to 10 years. You can make like one or a few and run some experiments. But if you wanted to make a trillion of them in mass parallel, kind of maybe similar to semiconductor fab. You tell me, Tom, I was at 10,
Well,
20 years off.
I think
I
I
don't know.
think what a lot of us are hoping for is the continual advancement in microscopy, because a lot of the concepts for mechanosynthesis, where you're actually using mechanical forces to place the atoms and provide the bonding energy to make these things. I think if you see the continuing trends, like the Q plus sensor for scanning probe microscopes was a huge advancement. Metrology uh, has come a long way. As long as those keep progressing, and people actually are interested in using these techniques to try to do mechanical synthesis. I'm not really sure if it's if the biggest roadblock is technology and like chemistry. Of course, there's the chemistry issue. You have to have, sort of exotic chemistry for feedstock molecules, where you can do this energy cascade from like your feedstock to your potentially a scanning probe microscopy tip to your work surface, to transfer those atoms like that in a precise way. I don't really see the roadblock being technology. I think I see it as nobody's trying, or very few people are trying. I'm aware of two groups. I'm aware of Moriarty in the UK, who's been working on silicon uh, mechanosynthesis for a very long time. And I'm aware of the Nanofactory effort, which is now the Canadian banknote effort. Outside of those two groups, I don't think anybody's trying. I think if there was a lot of groups trying and competing and trying to outdo each other, I think we could see it relatively quick. At least like one or two one-off special special machines, not like a mass production of anything by any means. But right, assembling 100 atoms in any configuration that physically possible, but any configuration that uh, you've designed atomically precise. I mean, what a monumental scientific breakthrough. But there's no application for that that I see, right? So I think you have to have people who think really far, far into the future. And other than a few visionaries, that's very rare to come by.
Yeah, I think it's a good point that we kind of, if we had something like the space race where
Oh man,
multiple
yeah.
countries, companies, everyone was just putting a bunch of R&D money into it, yeah, we could probably do this pretty soon. At least 100 atoms or something like that. But then to your points, like where's the ROI? What's the end goal when you look at drug development?
Yeah.
It's somebody's dying, they have this disease, we want to cure it, like we're going to make this drug, and look, there's this many people with this disease and their insurance is going to buy it, and we're going to make money and help people. So like people invest in that. But right now, if you just go out and you say, hey, investor or government grant, or whoever you want to fund this corporation, give us some money so that we could do all this, It's like what do they get in return? It's like I think there's going to be really great stuff eventually. There's
Mhm.
just no like
Yeah.
clear short-term ROI on the investment. It's all these
Yeah.
like bigger long terms. Like, of course, in 1,000 years, when we're a multi-planetary spacefaring civilization, we'll have like bottom-up atomic manufacturing precision.
Well,
It's
hopefully
like,
it's gonna
yeah,
happen.
eventually we'll have it. How do we get there?
And of course, the cost of doing this type of research and development is coming down all the time. If you look on the web for like do-it-yourself scanning probe microscopes, I
Mm.
mean, there are like a half dozen designs out there. I mean, could you imagine when the scanning probe microscope was first invented, that like someone's going to do this in their garage, right? So I mean, so as the type of uh, equipment and knowledge comes cheaper and cheaper to acquire, then of course the uh, the cost to do it comes down. That makes it more enticing for more groups to try.
Hmm. Yeah, I've told Kate this, but yeah, someday when I'm rich and retired, maybe I'm gonna have the electron microscope in my garage. It's gonna happen.
Yeah, for sure.
So my final question was, I guess, Tom, you've done these MD simulations of these various designs and structures before, and you've obviously seen them on a 2D screen. What was it like for you to actually see your trajectories inside of VR, and how was that like?
Oh, yeah, it was very evocative. I mean, it's just like VR in your technology. It's really something people have to experience to understand, but to put you inside of it. And I mean, like I'm thinking about, I have other systems that I didn't set them up for this interview, but they have like little channels and tunnels and machinery inside that you can't see from the outside, and I can't wait to actually try to load those and like fly inside of it to see like the inner workings of machines. I think that's going to be uh it I mean, it's an amazing experience, and just for like explaining to other people how things work. And I think that's really the key application. uh I'm not sure how I would design these things in VR yet, but as a communication tool, as letting people experience these things in new ways, I think it's been a really great experience.
And what's your current workflow for designing them?
So current workflow is, I still use NanoEngineer-1 about every day, all the way back from Nanorex. And then there's this other great piece of software called SAMSON, and these are basically molecular CAD programs to sort of design, get your structure together. And then I have a bunch of scripts that I've written myself that take that structure file and produce a simulation input file. I make all these things available too. I have a repo on GitHub that I hope people learn of and want to like download these machines and the input scripts and test them out, and you know, contribute new designs and modify them and all that.
Yeah, let's hop in and check it out in VR.
Cool, let's do it.
Yeah, so I thought this would be the first thing that we look at. So this is just kind of a simple spring, and the motivation for designing this, it's just one project in a multi-project program just to look at compliant mechanisms. And compliant mechanisms are, really great because if you can make those, you can really cut down on the number of parts that you have to assemble. So starting off, this is about as simple as you can get. The material, so this is all hydrogen passivated diamond, and this is hexagonal diamond, also called Lonsdaleite. And it's a little bit different than the diamonds that come out of the earth. Refer to that as cubic diamond, but this Lonsdaleite has a hexagonal unit cell. I find it a little bit cleaner to work with than cubic diamond. It really is my favorite thing to work with. And of course, diamond is just a great engineering material, all around engineering material. So as molecular machines go, this is about as simple as it gets. So basically, there's just these two pillars on either side, which are anchored, and then they are bridged here by these two rows of rings. Now, if you look, uh, the rows are connected by these pentagonal dislocations, And in my experience, diamond molecular machine design really comes down to being able to use different locations to shape and orientate the crystal lattice into what do you want it into what you want it to be. Uh, so if we let's switch back to van der Waals, because I think that looks really great. And then we can look at the simulation. Let's play it. Okay, so here we go. It's going down. So in this simulation, basically, I'm just using what amounts to an as an infinite force. So I use lamps as my molecular dynamics engine, and I'm basically just telling lamps push the center column down a couple of nanometers, release it, and see what it does. And of course, the spring springs back up. So springs are a fundamental mechanism to have. So if you have like some system that you want to return to first principles, of course, the spring's going to do that for you. And then, I like to imagine having larger, more complex nanoscale systems that have maybe large springs or mini springs in them. You might imagine like a nanobot one day that kind of works like a wind-up toy, right? So yeah, you wind up its spring, it goes and does something, and then you wind up the spring to power it again.
Yeah. I was just gonna do ball and stick because we talked about before the call here, we talked about the distances that we're dealing with here. So I guess from
measurements.
this time to this outer edge, there you go. That's about 47 angstroms, and then from the top,
31 by 47 angstroms. So yeah, like 3 nanometer by 5 nanometer.
Yeah.
And you can see
the travels with. Yeah, that's great.
Yeah. So that's kind of cool. So you can see essentially, so we go from like 48, 49, and then the top, you can see how much it compresses to, that's cool. If you go to that, at the shortest, it goes all the way down to 43 angstroms. So there's about like a 7 angstrom compression at the top there. At the widest, it's about 48.
Yeah.
And then when it gets compressed, right? Like right before it springs up, it goes all the way down to 42. So you can literally see how much the top gets compressed there. You know what I mean? Like the top end of this, like this part right here. So,
yeah, it's pretty cool. Well, that 16 angstrom side that you have, like that's undergoing 2 angstrom of change. Right, it goes from 16 down to 14. That's where the energy is stored, right? Like that's the actual functioning energy
right here
in the spring, right?
Yeah, in these sort of bridges that.
Yeah, the diagonal ones.
Yeah.
And that's a 2 angstrom delta. That just seems like a lot of energy being stored in those bonds.
Yeah. Well, yeah, I believe it. So, there's this great paper not too long ago by Dr. David Tomanek and his group. They were looking at winding up carbon nanotubes as energy storage devices, and they calculated that the energy density of wound carbon nanotubes were basically on par with lithium-ion batteries. So there's a lot of potential to store energy in these bonds.
Cool. Should we take a look at another structure?
Yeah, absolutely. So this is Lonsdaleite, and you can tell when you see these hexagons that kind of go all the way through the structure that you're looking at the 111 crystal surface.
Got it. All these right here.
Yes, yeah. So this would be the 111 surface of Lonsdaleite. Then again, I just have like this this pillar, some sort of piece in the center that's connected by these living hinges. And the way they're connected again is I have these pentagonal dislocations, and what that does is it gives you a nice row of single bonds, and those single bonds are actually acting as the hinges. And this simulation again, I'm just telling lamps, move it down to the bottom position and release it, and see if it stays there, and it does stay there. And the reason is there's this sort of mirror symmetry in the 1-1-1 lattice, where you have these rows, you have these diagonal rows that kind of go up in this direction, and this diagonal row that goes down in this direction, and that creates the two stable states.
Cool. Yeah, so I guess just like what we did during our last structure, I'll make a couple of measurements here. So
Okay.
just to get an idea of what kind of structures we're dealing with. This feels bigger than the other one.
It's bigger, but as what's interesting is when you have any sort of like bistable system, it makes a nice memory element, right? So when it's in one position, that could be a 1. When it's in the other position, it could be a 0. And one of the areas that I'm really interested in is mechanical systems that do computation. So it would be really great to potentially use this as a memory element in those systems. And when I first designed this, I wanted like some evocative tagline or some evocative piece of trivia that I could attach to it. So I asked one of the AI agents to kind of estimate for me, what is the data rate of the optic nerve in people, in humans? So like how much data goes from your eye to your brain? And the estimate they came up with, I have to admit I didn't fact check it, but the estimate they came up with was 10 megabytes per second. And so, I if that assumption holds true, what I did is I did a little back of the envelope calculation that a few cubic millimeters of these switches could store enough information to record everything a person sees in 100 years. So I
Wow.
thought, that's like really evocative for people who want to like upload their minds one day. They could potentially store their consciousness in these little bistable switches.
That's awesome. Just based on the measurements here, I guess this is actually almost 100 angstrom wide structure, and the structure here that's being sprung up is about 75 angstroms. The biggest variance I think we see here is the spring itself over here. Wow, that's just a lot. I just saw when it really gets compressed right there.
Right. So this is the one of the things. So this is part of feature work, is the way these hinges twist out of plane. Of course, that's to eat up some of the strain, right? Some of the strain of potentially being too long. So one thing I might do is you might need to cut down these hinges. They might be a little bit too long. This is really just a first version of things. So that's on the list of things to do. And then of course, if this was ever going to operate as a memory element in a computer, then you would also need the read and write machinery to go along with it. So this is a Ratchet and Pawl mechanism. So it's still Lonsdaleite, and we're still technically looking at the 1-1-1 surface. So in the ball and stick model, you can look through the hexagons, right? So you're looking at the 1-1-1. But in this instance, I've used 48 rings that have been strained into this ring motif that's held together by the central hub. And then maybe you can make out through the simulation that the hub is connected again with these pentagonal defects.
Yeah. Oh, yeah. I didn't realize. So there's this structure on this side.
Oh yeah. So this is just
well.
Yeah, so the hub actually serves as an anchor, and I use this strain ring motif quite often. So if you change the shape of the teeth here, they're sort of in a ratchet shape, but you can make a spur gear out of it. And this strain ring motif, actually, the larger it gets, the less strain there is, so it scales quite well. So I have 16 teeth gears that can all be attached on the same axle. And I even have a 32 tooth gear that can be, you can make little gear trains out of this for like speed reduction systems.
Yeah, this is an incredible thing. I'm now noticing how much this side is the one that, or this kind of structure here is what basically kind of like tightens the.
So this is where I'm applying the torque to actually turn the ratchet.
Right, and then it gets caught there, and then
Yeah. So first of all, it goes in one direction, and it slips past the Pawl, and then in a separate simulation where the trajectories have been combined for this, it rotates the other direction, and then the Pawl stops it until eventually the Pawl does slip past. But in this instance, it is getting like a near infinite torque, so it's it's not quite fair for the Ratchet.
as we've been doing in the other structures, I figured we could do a kind of a measurement there. And by the way, it's really it's much easier to select individual atoms for me when I blow it up like this. So
Yeah, wow. I mean, that looks. I've never seen like one of my machines this huge. This is amazing. Amazing to see it from this perspective. It really is.
Yeah. Yeah, and then
So it's the opposite, right? It's like everyone expects you to be like looking at some microscope and like
Yeah, for
tweezers,
sure.
right? Now it's like a
To see it
skyscraper.
like the size of a wind turbine or something is amazing. So this Ratchet design, I guess maybe I'll mention while you're taking the measurements. It's sort of a starting point because what inspired me is years ago I came across this movement by the Seiko watch company, and they call it the magic lever, which is actually a ratchet, but it has pawls on either side of the ratchet, and the way the pawls and the teeth are shaped, it doesn't matter which pawl interacts with the ratchet, it's still going to only turn in one direction. And I think the idea was Seiko was going to use it to energy scavenge to rewind their watch. And I thought, hey, that would be really cool if that scales down to the nanoscale, because then maybe you could power more complex nano systems or wind torsional springs just by with like waste heat and vibrations in the environment. So this is a starting point, but there's a lot of work to get to something like the Seiko magic lever. Wow, that is amazing.
yeah, it's kind of too big. But yeah, it looks like the total measurements are smaller than the previous one because like it really, I mean, I think what they go
Yeah,
the longest like 75 angstroms long.
I mean, this isn't like if you do DFT calculations on strain rings, this is kind of close to the smallest diameter you can get for like an SP3 bond.
Mhm.
If you go any smaller with the SP3s, then you start to introduce a little too much spring. Of course, the hub helps.
Yep. And I guess on this side, I also wanted to see kind of, the relationship because it's this kind of structure here is what's applying the torque. I kind of wanted to see how much it independently moves from it, and you can kind of see that when it gets diagonal.
What? So the torque is being applied to this hexagon part back here.
Mm-hmm.
This ring in between the wheel and this hexagon that's actually a carbon nanotube that acts as a bearing.
Mm-hmm. This part right here, right? Yeah.
Like right in there, and this outer ring. So there's two there's a ring, and then the axle is actually a hexagon, which if we switch to van der Waals might be a little more clear.
Yeah.
So this darker gray is
wow, yeah. Actually, the van der Waals really helps a lot with deciphering. Yeah.
So you have like a hexagon in the middle there, and then you have like 6 like lever points out, but then you have
spokes,
eight gears. So you have 6 spokes and 8 gears. What went into that design choice?
So, as long as there's 48 rings around the circumference of the wheel. So as long as your spokes and teeth are as long as 48 is divisible by that number, you're generally okay. So you have equal spacing between all the different parts, like the different equal spacing between the spokes, equal spacing between the teeth.
Yeah. Have you thought about doing 6 gears? 6 actual bits?
6 gears with 6 teeth?
Yeah, 6 teeth.
Yes, I have. So in the part library, there's a I call it the pinion gear, or also I call it the snowflake gear.
Uh-huh.
And I have a lot of systems that do use the 6-tooth gear.
That's cool. What about like the 12-tooth gear?
Oh, I don't think I've done 12. So I've done 6. This is 8. I've done 16, 32.
Yeah.
Right? You see the
Exactly. Okay. So
yeah.
so you've pretty much just been playing with 48 and like all the visible.
Yeah, the multiples of 48.
Cool. Okay. Yeah, no, that makes a lot of sense. Yeah, that was one of my questions.
Cool. All right. So I guess I'm just gonna trash this, and then we can load the last
Yeah.
structure here.
You want to do the last one? Yeah, so this is, this is a rivet. So I was really interested in developing some mechanical fasteners. Like if you think about it, all these parts are going to have issues of sticking together anyway, just through van der Waals forces. But depending on your application, you might want like some stronger connections. So this is a rivet design. So
Okay.
this is the cap of the rivet. So again, this is the 1-1-1 surface. By now you can probably make out the hexagons, little hexagon trying to. Then we sort of look at the barb portion of the rivet. And now again, if you look at the barbs, we're looking at the 1-1-1 surface, and the 1-1-1 surface makes carving things very nice. So we saw that in the Ratchet. Now we're seeing it in the Rivet. But if you look, maybe we could pause let me pause the simulation for 1 second.
There you go.
Okay. So yep, that'll work. So if you look, there's a set of dislocations here. I call it the 5-7-5 dislocation. And basically you have a heptagon, pentagon, heptagon, and then there's another pentagon. But generally I refer to this as the 5-7-5 dislocation. And if you do this type of work a lot, it's a very handy thing to know, because it allows you to orientate 1-1-1 surfaces orthogonal to each other. And that's very handy, and that need comes up a whole bunch. So I think that's kind of like the most interesting thing about the actual design techniques, the build techniques of this rivet. So now that we have our barbs, we just kind of go into the socket. And for this simulation, that's basically all I did. Is I've inserted the rivet into the socket, and then I release it and it stays in, of course. But I have done subsequent simulations after this where I actually measure the force needed to try to extract the rivet, and it basically breaks. So it breaks right where the cap meets the neck, right there, kind of like at the narrowest part. And that takes like 5 nanonewtons to do, which 5 doesn't sound like a lot, but when you're talking 5 nanonewtons over this type of area and this few atoms, that's actually like really impressive strength. So I'm excited that I have like this really nice clean mechanical fastener. I have like a big plans for it, so I'd like to use the 1-1 surface, 1-1-1 surface here on the front, basically to mount a whole bunch of different other types of parts and structural elements, and basically just have a whole library of things that can snap together. So that's kind of like the long-term plan for this little humble rivet. I'm running some simulations now where I've actually added a little handle to the top here, and I have this little nano gripper that's like pushing the rivet, and the barbs are longer, and it's pushing the rivet, and it's trying to fasten 2 beams together. So, and if that works out, I'm sure it'll work out eventually, but sometimes it doesn't work out on the first try. But when that works out, that's kind of like the first time I've ever used a machine to assemble other machine parts. So it's kind of like a really exciting simulation for me, and it's currently running. So maybe we can look at it at some point in the future.
So I'm gonna go ahead and make a similar measurement here, like we did with the other structures. So it's about 50 angstroms wide, and then I guess from this side to the furthest part here, I guess, oh yeah, interesting, 50 by 50, and then and it just comes really close, collapses in that that distance. Although I guess this isn't, it's a rivet, right? So we're not really trying to get a lot of torque and distance changes per se. I guess it would be interesting to see how much this moves out. This part moves out.
Well, I
Yeah,
think
so
maybe the
I
planes,
mean,
like
this
the middle
socket's
of
just kind of like a stand-in. So I would, you would never really have one row of hexagons, but this is just kind of an early test.
It's cool.
Yeah.
What would be the force it could hold if you had like I don't know, a 1 square meter,
1 square
like
meter. Yeah, that's.
1 square meter of these things, how much?
I mean, it's going to be way stronger than any weld. It's going to be stronger than any sheet of stainless steel. I mean, I couldn't think of a mechanical fastener that would be stronger than a whole bunch of carbon atoms.
Well,
Uh,
maybe just back of the envelope, this is like 5 nanometers, and so we just multiply it by a billion. You said there's 5 newtons.
well,
Or-
yeah, but that is sort of the failure point for that is kind of arbitrary, because you can make the part where the barbs connect much larger if you wanted to, and distribute that force over more bonds.
yeah, true. It's like, what's the failure point? You're pretty much just looking
Yeah,
at
yeah.
failure point of a sheet of carbon or something.
This is so mesmerizing. I'll never get tired of looking at these trajectories.
Oh, you guys
It's
got to
so
see
cool.
you got to see the grippers, man. The grippers are really popular when they like pick up little nanoparticles and move them around, and it's those usually get quite a bit of attention on YouTube.
That's really cool. So just gonna zoom in and say, so that the failure point is basically here, right at the top.
Yeah, right where you looks like
right
you're looking.
there. And then the attachment point is going to be this whole plane on the top.
Yeah, it could be.
Pretty much functionalize it with like anything. It could be
Yeah,
proteins.
Well, yeah, yeah, for sure.
Maybe somebody in our life sciences and biotech community will see some greater purpose with some of these structures of having some sort of a sensor or other synthetic biology creation with this.
Wow, this is awesome. These structures have been like very different for all of them, and so it's kind of fascinating to just see, how much variety and kind of potential there is.
Thank you.
Right.
Yeah.
At the scale.
And I have like many more, like, we mentioned in the interview that all this is available in my repo. If people are interested in this and they'd like to learn how to do this type of molecular machine design, I find teaching people about it, setting up the tools very interesting. So, I hope this gets people interested in that. They want to work on these things, and we can get basically a whole little team of molecular machine designers together for the future.
But this is really awesome. Appreciate that you're doing all this work. And
well, I appreciate your guys' interest, and thank you for inviting me to talk about them.